After adding the gene annotation to the Seurat object, now we need to perform the quality control. So a question is, why we need to perform the quality control? We need to perform the quality control because single cell ATAC-seq data is noisy and variable, and not every cell or barcode that passes cell ranger filtering criteria is a real or high quality cell. Similarly, many barcodes come from empty droplets or damaged cells or doublets and multiplets. If we do not perform the quality control, then these bits or low quality cell can disturb the clustering, and similarly it will not be able for us to see the real biological differences, and it will lead to the wrong results for the motif enrichment and T transcription start site enrichment analysis, and that is why we need to perform the quality control. Now let's get started with the quality control. So first of all, we will compute the nucleosome signal for each cell. So compute the nucleo signal score per cell. So we will use the given line of code PBMC, which is our Seurat object, and we will use the nucleosome the signal function from the Signac package. So nucleosome signal function and Seurat, run. This line of code will compute the nucleosome signal score for each cell. It will take some time because there are a lot of cells, so it will take some time. Now the nucleosome signal score for each cell type has been calculated. Afterwards, we will calculate one of the most important quality control metrics, that is the TSS enrichment score for each cell type. So we will calculate the start site enrichment score. So we will use the given line of code, so PBMC, which is our Seurat object, and we will use the TSS enrichment function from the Signac to calculate the transcription start site enrichment score. So PBMC and the key parameter include the fast false, which will be slow on large dataset but very efficient. So run. It will take some time. Finally, after taking some time, the TSS enrichment score has been calculated, and now we will look into the TSS enrichment score across few cells. So TSS enrichment score across few cells. So we will use the head function PBMC, and then we will access the TSS enrichment slot and run. You can see the TSS and enrichment score has been given for few barcodes or cells, and now we will visualize the peaks region fragments. So we will make a violin plot. So visualize peak region fragments. We will make the violin plot by using the violin function from Seurat. So TBMC features, and run. Now you can see the peak region of fragments distribution across the cell by the violin plot. Now we will manually calculate and add the PCT reads and peaks. So calculate and add which is one of the most important metrics. So now PBMC, and then we will access the PCT reads and peaks. Peak region fragments. And run. The PCT reads and peaks has been calculated and added to the Seurat object. And for your information, let me tell you that the peak region fragments are the usable fragments, and the passed filters are those filters that has been passed from all the quality control from cell ranger. Now we will add a black list ratio to the Seurat object, which is a new metric, and so add a black list ratio. To the Seurat object. A black list ratio is a ratio between the black region fragments and the peak region fragments. So it is a ratio of black region fragments and peak region fragments. So now we will add a black list ratio. So PBMC add black list ratio. As it is the ratio between black region fragments and peak region fragments, so we will access these two metrics one by one. So Blake region fragments and PBMC, and now we will access the peak region fragments and run. The Blake list ratio has been added to the Seurat object. Now question is why we need to add the Blake list ratio to the Seurat object. We need to add the Blake list ratio to the Seurat object because it's one of the most important QC, and it computes the peak signal that come from the Blake that comes from the Blake listed genomic region. So we need to add this. Now we will check that whether the Blake list ratio has been added to the Seurat object or not. So we will check. So we will use the head function, Blake list ratio. As we can see from the console that the Blake list ratio has been added across many cells. Now we will create a group based on TSS enrichment threshold. So create a group of TSS enrichment threshold. So now we will add a new column to the Seurat object named TSS high. So is equal to F else PBMC TSS enrichment. So the 2 will be used as a threshold value. So if a cell scores greater than 2, then the cell will be labeled as high, which means a strong promoter enrichment, and if the value is lower than 2, then the cell will be labeled as low, which means a flat promoter enrichment. So now we will run the code. Now we will visualize the TSS enrichment by high and low group. So visualize the TSS enrichment by high and low group. So we will use the code. We will use the TSS plot function from the SIGNAC package, which is the inbuilt function from the SIGNAC package. So Seurat then we will split the two group based on the higher.tss score. So group by and run. The plot has been generated, and there are two types of curves, and similarly the x-axis shows the distance from the TSS group, and the y-axis shows the TSS enrichment scores, and the high curve shows the high quality cells with strong promoter accessibility and open chromatin region, and similarly the low curve shows low quality cells are in empty droplets with a closed chromatin or weak promoter accessibility. Now we will group the cells based on nucleosome signal score. So group the cells based on nucleosome signal score. So Seurat, we will add a new column to the Seurat object, and that is a nucleosome group. So if else, then we will access the nucleosome signal column from the Seurat object. So nucleosome signal, so if the nucleosome score greater than 4, then the cells will be labeled as NS greater than 4, and these are usually considered as a low quality cells. And if the nucleosome scores smaller than 4, then the cells will be labeled as NS smaller than 4, and these are considered as good quality cells. So run. And finally, we will visualize all the quality metrics by a violin plot. So now we will create a violin plot by using the violin function from Seurat package. So violin function and Seurat features, and then we will pass all the metrics one by one. So nucleosome signal, and TSS enrichment, and peak region fragments. PCT reads and peaks. Blacklist ratio, all the plots will be grouped horizontally, and run. The violin plot has been generated. Let's zoom in the violin plot of all the 5 quality metrics. So you can see the violin plot. The nucleosome signals violin plot shows that most values are centered around 1 to 4. And similarly, the TSS enrichment violin plot shows that there are few cells with weak promoter enrichment that need to be removed, and the peak region fragments violin plot shows that cells with greater than 40 or 50,000 need are the potential candidate for removal. And similarly, the PCT reads and peak violin plot shows that almost no cells with smaller than 20%, that is a good indication. And also there is minimal or no sign of blacklist contamination, and that is a good indicator. So we will now create a Seurat object. So we will create a subset of the Seurat object based on this criteria. So create a subset of Seurat that will only have the high quality cells. So PBMC subset function PBMC peak region fragments. With value greater than 3000 and smaller than 20,000 will be removed. Only the peak region fragments with value greater than 3000 will be retained. Peak region smaller than, so the peak region fragments will be retained with values between 3000 and 20,000. You can set up the filtering criteria according to your data set and research hypothesis. So now the PCT reads and peaks with value greater than 15, and the blacklist ratio value 0.05, and the nucleosome signal smaller than 4, and the TSS enrichment and run. we have made some mistakes, so and now run it. So the subset of Seurat has been generated, and now this Seurat will contains only the cells that fulfill the above criteria. So you can set up the filtering criteria according to your research hypothesis and dataset. Now we will normalize the peak count matrix using the run tfidf function, which is a standard function and is widely used for the normalization of single cell ATAC-seq data. So normalize the peak count matrix using the run tfidf function. So pbmc run tfidf function. Normalization of the peak count matrix has been finished. Now we will identify the most informative peaks that differ between cells. So identifying the most informative peaks that differ between cells. So pbmc, which is our Seurat object, and we will use a find top feature function. The key parameter include the q0. You can change according to your hypothesis the value of q, but we will keep it 0 because we want all the features. So run. Now we will perform a linear dimensional reduction on the normalized peak count matrix, so using the svd function. So linear dimensional reduction by svd, which is a singular value decomposition. So pbmc run svd and pbmc, which is our Seurat object, and run. The normalization of the peaks count matrix using the run svd function has been launched and it's running. Finally, the svd normalization dimensional reduction has been completed, and now we will make a correlation plot between the lsi component and the total sequencing depth. So create a correlation plot between LSI component and total sequencing depth. So we will use the depth function from the Signac package, depth core function, and PBMC, and run. You can see the correlation plot. The first LSI show a strong correlation, and so we will remove that and our downstream analysis. And now all the remaining codes are similar to the single cell RNA-seq analysis. So I will copy and paste all the remaining codes. So paste. There is only one difference, and that is the removal of the first LSI component that showed a strong correlation. So now we will run all this code one by one. So first run UMAP. The code is running. And now we will find the neighbors. So run. And now we will run the find cluster. And finally we will visualize the cell clusters by using the dim plot function. So run. You can see the clusters has been generated, and almost there are 15 clusters in this data set. And finally, all the standard workflow, quality control and filtration process for the single cell ATAC-seq data has been completed. And now we will save the Seurat object for future use. So we will save the Seurat object. So we will use the save RDS function to save the Seurat object. So PBMC dot RDS. So the Seurat object has been saved, and we have reached a solid checkpoint, and now our object is ready for the next exciting part.